Yeah, but you're only B, but still such a good thing.
I have an 89.3.
All right, ladies and gentlemen, recording has started. I wanted to start early today because there is a lot of information stuff that we need to go over at the beginning of class today for people that aren't here. So, first, calendar. Today, we are going to put some terms and definitions on a bunch of the things that we saw on Friday down at our demonstration in the PAC. That is going to wrap up the beginning of this unit on mechanical waves. And tomorrow, I'm not going to be here. But you are going to take a quiz tomorrow, okay? So, it's an open note quiz, right? It's a homework quiz. I'll have the sub give it to you. I'll have the sub give you guys about 20 minutes or so to work on the quiz. Then I will do a short recording getting us into the next part of this unit based on sound and hearing. And I'll have you guys watch that after the quiz on Tuesday. Yes, Doc?
That's tomorrow's blue.
Tomorrow's blue because I am not going to be here. That's like a reminder to myself that I'm not going to be here. So just when things are highlighted in blue, those like reminders usually to me, like, oh hey, don't do something here, or don't do something there, or something like that.
What about the test last week?
Test is still kind of in. This is exam stuff. So.
Oh, that's
Please tell me it's not Mr. Bindernagle.
It's not Mr. Bindernagle.
Yeah,
Mr. Roby.
Oh my god!
he's my favorite.
Mr. Roby. Kirsten.
He's my favorite.
Do you want to know who was subbing? So yeah, Mr. Roby claims.
Can you highlight the test?
I love
Because Sam, I'm not sure it's going to be on Wednesday. It's going to depend on how far we get on Tuesday and how far we get on Wednesday. Well, you know, that's kind of the thing. So.
I mean,
Monday.
Save it.
my final.
Then for the rest of the week, we're back on block this week. This is our last week of block. So on Wednesday, we'll finish up the sound stuff that you hopefully will get into on Tuesday. Then we'll introduce electromagnetic waves, which have some things that's similar with mechanical waves and some things not. But then, towards the end of class, there is a Magic School Bus episode that illustrates some principles of color that I like. I think it does a pretty good job. So we'll finish up our block day watching Magic School Bus, and then we'll sort of wrap that stuff up on Friday, review Monday, test Tuesday, kind of the plan right now, but we'll see how that goes. Okay?
Review Tuesday, test on.
Say again?
Review Tuesday and test on.
Maybe. I mean, that's what I
You
want.
said review Monday. Test
Oh, sorry. Review Tuesday, test Wednesday. Yes. No block next week.
We're spending our last block of our freshman year taking notes. Like, for a little bit of time, we're watching that.
So
Oh, that's exciting.
just watch Basic School Bus.
No, that sounds pretty good. I'm good with that.
We don't have to take
Magic
notes.
School Bus is only like 22 minutes long.
Yeah, so
We
watch
don't
it.
have to.
Is it better quality than the other one?
Like
That
a
was
fun
pretty
activity with it.
Hopefully not. I think actually this Magic School Bus actually I have it like saved on my jump drive, so I'll play off of my jump drive as opposed to streaming it.
It's like Jeopardy. Oh, it's like that.
We have to get through some things, so that's issue that we have. All right. So let's finish up, or let's get into the next section dealing with the interaction of waves. On Friday, down in the PAC, we did a bunch of demonstrations dealing with looking at what happens when waves interact with one another, what happens when they encounter each other, what happens when they encounter other things. Okay? First, just for a little bit of review, on Friday we were dealing with mechanical waves. If I say something is a mechanical wave, there are two things you should be able to tell me about it. Chris, what's one thing?
Let's travel through media.
Has to travel through media. That's the mechanical part. What's the wave part? What does it mean if it's a wave? It's a disturbance that transfers energy from one place to another. Okay? How waves interact and how waves behave around other things is a little bit different than the way that other things do, because waves aren't matter, right? Waves are energy. You have to keep that in mind when we talk about what happens to them in certain situations. Okay? So, the first thing that we saw on Friday was the idea of reflection. Okay? By definition, reflection is a wave bouncing off of the surface of something that it cannot pass through. How does a wave travel through a medium? What has to happen in order for a wave to travel through a medium?
Like all the particles have to be able to like contact each other.
Good. And by the contact, what are they doing?
Just like distributing each other.
They're passing what from one to the next?
Energy.
They're passing that energy from one to the next. And that will continue, right, until either the medium runs out or it encounters something that it can't pass the energy to. In the case of the spring, one coil makes the next coil move, makes the next coil move, makes the next coil move until it hits somebody's hand, right? And the people down at the other end reported that their hand did move a little bit, but it's not as easy to get somebody's hand to move because of the muscles and stuff like that as it is to make that next coil of the spring. So instead of all that energy passing into the person at the end, it bounces off of that person and starts heading back in the other direction through the medium which it came. Okay? How something bounces depends on how it comes into the surface that it bounces off of. We refer to this as the law of reflection. The wave will bounce off of a boundary at an angle that's the same as it approaches the boundary. And this picture here illustrates that point. Sorry, there was a lot of pictures here and I wanted to get them all on one page, so I kind of squished them in. Yes, ma'am. Yes. When you play putt-putt, you know how you sort of play the angle off of the way that it's going to hit the wall. Or if you play pool or something like that, okay?
Wait.
Yes, that's exactly the same thing. That the angle that it comes in at, it will bounce off of that boundary at the same angle. Okay? Now, sometimes like when you play putt-putt, it gets a little complex because the wall isn't exactly straight, right? Sometimes it's twisted, it's like tilted as well. So, you know, but those are the things, but yes, that idea is the same. So we refer to that angle I, we say that this picture here, incident pulse, the one down labeled down here. Oop. Incident pulse, that's like the wave that's coming in. Reflected pulse, that's the wave that's going out. So we say that the angle of incidence, the angle at which it comes in to the boundary, is the same as the angle of reflection, the one that comes out of the boundary. But yeah, pool, putt-putt, same idea. That you try and hit it at a certain angle so it will come off at the same angle so it goes where you want it to go. Okay, good example. All right, we're good there? On Friday, we saw, well, let's do this first, okay? A reflected wave has the same speed, frequency, and wavelength as the wave did when it was coming in. It's the same wave. It's the same energy. Okay? Illustration. When you hear an echo, what does the echo sound like? It sounds like you. Why? Because it is you. It's the same wave that you created just coming back to you. Right? Amplitude is a little different, though. On Friday, we saw something that we called a fixed end reflection, where the medium was attached at one end, that by somebody holding their hand. And we saw that what happens to the amplitude of this wave when it bounces off of that fixed end. It gets smaller, but that's not because of the reflection. Hold on to that for a second. But did we look at which way the pulse was facing? Was it facing the windows or was it facing the PAC? And when it got to the end, it flipped over onto the other side, right? Fixed end reflection means the amplitude gets flipped from one side to the other side, okay? Of the medium, or more of the rest position, right? So where the spring was before the wave started passing through it. I mean, and so like if we like made the pulse on the one side, on the Windows side, when it went down, it came back on the other side, on the PAC side. Also, we also saw that what happens to the amplitude as it's bouncing off and coming back. It gets smaller, but that's not the reflection's fault, right? That's because what happens to the amplitude of this wave as it travels anyway. It gets smaller because it's what? It's losing energy. Okay? Good there? Next. Oh, amplitude's usually lower. Why? Because it's losing energy as it goes along. The amplitude isn't necessarily lower because of the reflection. Sorry, good word. It's just lower because it's losing energy through friction and stuff like that. Yes, sir.
So is the amplitude like how tall the wave is,
Yep.
or how big? Like
Well,
how, like,
no, it's more up and down, not side to side.
okay.
Okay, so if we take, right, let's take this for example. So Austin, this is like a time lapse photo, right? It's a bunch of pictures that were taken like like every 1/10 of a second or whatever. Okay? So here's the wave as it's coming in, and it's traveling in this direction. Okay. Now, I use the blue arrow, right? Actually, I should probably go here. Okay. But now, if I take this blue arrow and come here, what do you see about how long the wave is? It's the same. That's what? What measurement of the wave is that? That's its wavelength, right? That's not going to change as it goes along. Okay, that should be the same. But also, too, after it gets flipped back over and reflects off the other side, what should we be seeing about the wavelength? It's the same, and I think we can see that here. Okay, but if you look, how much space is there between my blue dotted arrow and the top or the bottom of the wave here? Not a whole lot there compared to like here, right?
So that's the
That's the amplitude that's getting smaller. Alex, good.
Forgot what frequency is.
Say again.
What frequency is.
You forgot what frequency is?
Yeah.
Frequency is how many waves there are per second, okay? Which is related to wavelength, how big the wave are. It's all some ways of kind of measuring how big a wave is or how many waves there are in a certain space, something like that. Okay? Caroline, go ahead.
For wavelength,
Yep.
you know how on most of the pictures we were looking at, the wave would go like under.
Technically this is how many waves.
Like, is it half?
This is only half of the wave,
Okay, that's what I'm
right?
thinking. So the
So
wave
technically, good.
would be like, it would include the distance of like the under one. As well.
Right. So that blue arrow technically isn't the wavelength, it's actually what? Half of the wavelength. Okay? But Sam, that's the idea I wanted you to get, that blue line is helping us look at the wavelength. Technically that isn't an entire wavelength, it's only half of a wave, because it's only half of the wavelength is only half of a wave.
So a wave would be like bang.
Yep, it's gotta go up and down. Okay? Anthony, go ahead. You good? Okay.
Sorry, I just.
You're allowed. Alright. Next. Refraction.
Wait, so Mr. Pence, is the quiz chart gonna be on like this too?
Yes, a little bit. It is open note, yes. Alright, so refraction. Refraction is the bending of a wave caused by a change in speed as it enters a new medium. The biggest thing being here with the refraction is the change in speed as it enters the new medium. We didn't actually see refraction on Friday, but we did see a change in speed as a wave entered a new medium, right? Okay. We saw that when we had the two springs attached, the one small spring and the one bigger spring, and we saw that as that disturbance passed from one to the other, there was a definite change in how fast the wave would travel. Okay. Refraction is based off of that idea, but it sort of works at an angle. Okay? Example, how many of us are in the unfortunate situation at home where we have to cut the grass? Anybody? Wow. 3, 4 people. Some, you're not allowed to?
No, I did it once. No, I did it once.
Yeah, no, same with me.
I did it once in the line. My brother had fired me.
Gotcha. I mean, there is something to be said for that thing. If somebody like drafts you into a job that you don't like, just do a really crappy job. And, yeah. I think my wife takes that approach when she does the dishes. So.
This is on
But
recording.
anyway, my wife is a self-admitted bad cleaner. Like she's just.
Your wife is
I am
excellent.
So she probably. Not all of it.
Do you have like OCD?
When I clean something versus when she cleans something, there's a definite difference.
We're recording this,
I
but
can't
Are you
like
the ice cream family?
No, my wife is not clean.
Yeah.
But yeah, see, my wife is definitely the cook, but I'm definitely the cleanup after the cook.
Okay. At least it balances out.
Yeah,
You got, like,
that's
this
great.
grid.
So, But that's one thing. Like when I do cook, I like do dishes along the way. Like if I'm like if I'm making something and like if something else is cooking, I'll like wash the pan that I used before.
Oh.
My wife doesn't do that. She just lets it pile up in the sink and then like.
You definitely have like a bit of OCD.
You have like an OCD.
Yeah,
You should check
look
that
at
out.
this room. It looks like pretty much like I have
Well,
OCD.
isn't it just your room? Well, yeah, looking at your
It's
desk.
like
it's
if I were to try, if I were to draw a dot on the floor, would you try to erase it at one point?
No.
Like when it
I
would just try
let
to erase
Allison
it.
keep this up all the time. So I mean,
What, the hive?
even though it's not funny. It wasn't even really funny like 4 weeks ago. But it's definitely not funny now.
Especially if she writes it every single
Every day. She writes EG.
And then
But-
students, please do not write on
Yeah.
Right next.
But
student girl.
the point I'm trying to make here is, if you're along the edge of the grass and you have like 2 sets of wheels on the sidewalk and 2 sets of wheels on the grass, you kind of get that idea where like one set of wheels wants to go faster than the other set of wheels. You sort of get it starts turning a little bit. That's what happens with refraction, is that one part of the wave is going faster than the other part of the wave because it's in a different medium. And that means that you get this bending effect because of the idea that you have one part going fast, one part going slow.
How does that happen?
Because it happens because the different mediums will transfer waves at different rates, right?
So there's like 2 different mediums at 2 different rates.
Yeah, pretty much. Okay. For example, Allison, here, picture. Okay. This isn't the best picture in the world, but the good example of this is that when you look, okay, if you're standing on the edge of a pool, right, and you see something in the pool, and you dive in to get it, when you dive in to get it, is it there anymore? It's not. Okay? Or at least it's not where you thought it was.
Oh,
Okay.
I was
Sorry.
like,
It's still there, it's just not where you thought it was. Okay? So, edge of the pool, water.
make sure
Okay.
it's deep enough to dive in.
Make sure it's deep enough to dive in, kids. Okay? And then here's said diving ring. Okay?
Make it
So, the diving ring, light comes in from the outside, it bounces off the diving ring, and it bounces back up to the surface of the water. Okay? But when it goes from the water into the air, there's a change in speed. And because of that change in speed, the wave bends, and now it travels sort of like in this direction. Okay? Then here you are over here. Okay? And that light reaches your eye, and you go, oh, I see the diving ring. So you jump in. But your eye sees this beam of light. So it transfers back, and it goes, oh, that diving ring must be right here. Because your eye doesn't know that the light bent when it went from the water to the air. It just sees the light coming and goes, okay, you know. But if your brain, okay, if you're ever like, anybody ever see Lost or not Lost? What's that Tom Hanks movie?
Castaway?
No, Castaway.
Oh, yeah.
Castaway, right? If you're ever on like that island, you have to like spear fish, right? You know, don't throw your spear at the fish over here. The fish isn't here. It's here. Okay? Just so you know, all right?
I don't think that we have, like if you're over there, if we were like water, you see the top of the water.
Oh, well, yeah. And that was because of, the reason I did that was because I didn't want to draw my person this tall, because then that was it's like the diving ring is bigger than you, so that's why I did that, because I didn't want to draw my person that tall, so you know. But yes. Anyway, but this is refraction, because this beam of light, the dotted red line, is bending as it goes from one medium to the next medium.
It's just like the
Wait, so how is there different? I don't get like how there's 2 different
Go
mediums.
faster, slower with it.
I don't get it.
Water, air, right? Light traveling through water is one medium. Light traveling through air is a different medium. And there's a change in speed because of that change in medium.
Okay.
Okay? Good.
I still don't get what like the bending of the wave is, like with the slinkies.
In the slinky, we didn't see the bending of the wave. In the slinky, we just saw the change in speed. But notice here, okay, because in this case, this wave is hitting the change in medium at an angle. If you were standing here, There's another diving ring, okay? And the light is bouncing off of it like this, okay? It all depends on which angle it approaches the bend or the change in medium at. Here, yeah, there's a change in medium from water to air, but there's going to be no bending here because it all changes speed at the same time. It's like if you're cutting the grass and you hit the the driveway or the sidewalk all at the same time, you don't have the lawnmower trying to turn because both wheels are going the same speed at the same time. Does that make sense?
Yeah.
Okay. So yeah, it depends on what angle you hit the barrier at. Okay. If you hit the barrier straight on, or if you hit the barrier being the change in medium from one to the next, if you hit it at the same time, you won't see the bending. It will change speeds, but you won't see the bending. Okay. Just like that's what we did on Friday. The springs, the two springs were straight, so we hit it at the same time. There was just a change in speed right away, but we didn't see the bending then. Okay, does that make sense?
Yeah.
Okay. Also good.
Is the wave going faster in the water or
Technically, a light wave. And this is kind of weird. It makes light waves different from like mechanical waves. Light waves will travel slower in the water than they do in the air, but mechanical waves like sound will travel faster in the water than they do in the air. Right? That's difference in the nature of the waves.
Do we need to know that or?
Not now. Not for tomorrow's quiz, no.
Oh.
Okay. Parker, go ahead.
How do you determine the angle at which it refracts at?
That gets into there's a couple of things that go into it, okay? One, it's the angle at which it hits the boundary, okay? But two, it also depends on what is it coming from and what is it going to. So the two mediums that it's going into, that it's passing between, also play a part in that as far as how much it will refract. That's a mathematical formula that you don't need to know. It's called Snell's law, but you don't need to know. But there is a mathematical formula that takes into account the angle at which it approaches, but then also the index of refraction, which is a measurement of these two materials to find how much does it slow down, how much does it speed up. Okay, Chris, go ahead. In this case, in this example, because it's light waves, this is actually slow to fast. Okay? If it was a mechanical wave, it would be fast to slow. But in this way, when you're talking about looking at diving rings, those are light waves, and they behave differently than mechanical waves do. Kirsten.
Okay, so for like the blue example.
Yep.
Like how you really usually see where the
If you were if you're kind of like leaning over the edge.
Yeah, so like if you saw like a red like that, like a blue would kind of be like all the way over farther than red. Like would you really see it there?
If you were looking at it more like this, Kirsten, like this, if you were like leaning over the edge like that, you would see it like there. It would be in the same spot because there is no angle at which it's approaching the barrier, or the angle is 90 degrees. Right, that's the key. Right, but now in this case, Kirsten, if we're there's no angle. But that would be like if you were leaning over the edge. Okay. Okay, so
it's the same concept as like if you put a pencil on the basketball.
yes, exactly the same concept. Yeah, because then the light waves that are coming from the top of the pencil don't have to travel through the water, whereas the light waves that are coming from the water have to go from the water to the air. So there's a change in speed, and you see that bending. Okay. Yeah. Does everyone know what Grace is talking about?
No.
Yeah, if you have a glass of water and you put a pencil or a straw, it'll work with a straw too. It looks like there's a break in the straw at the surface of the water. It's not really broken. It's just the waves from the straw that's in the water have to bend as they come out of it. So more water would probably help.
It's hard to
I can see it from here.
It's hard to all the time. You're like, it's hard with
Yeah.
Yeah, how are you gonna get that out?
Oh yeah.
She sacrificed it for science. Okay. Next. Don't worry about those last two. So, because it's advanced concept, and I really want to try and get through this, but we're not going to anyway. But that's okay. Actually, here, I'll do it this here. There you go. What it says.
Well, I
When a wave goes to a more dense material, it bends towards the normal perpendicular line. The normal perpendicular line is a line that goes straight up from the surface, perpendicular to the surface. Okay?
So one in the words,
It depends on how it just depends on how it bends. That's all. Okay? So, like in the case of this, if you're looking at the tree out the window, it actually affects twice. One when the light from the tree goes into the glass, and then once when it comes out of the glass.
yeah, so the tree not there.
In that case, well, the tree is definitely here because I'm looking straight out the window. But if you look at the side, there is some difference in probably where you're seeing it and where it actually is. All right, next diffraction.
And superposition.
Yeah, those are two separate subjects. So diffraction, bending of a wave as it moves around an obstacle or passes through a narrow opening. We did not see this on Friday. Okay. The best example I can give you of this is if you're walking in the hallway and you're coming up to an intersection in the hallway. Can you hear what's going around the corner? Can you hear what's going on around the corner? Yeah. Okay. If okay. So here's red guy. He's walking this way, right? Okay. Here's blue guy. He's walking this way. Okay. If blue guy is talking, he's creating waves that look like this. But they hit the wall over here and they can't go any farther. But as soon as they get to the corner, when there's no boundary there, those sound waves start fanning out around the corner. So now red guy can actually hear what blue guy is saying. If he's talking loud enough, yeah. Okay. Now, with that, we're trying to prevent diffraction from happening because once we get here, right, waves are energy. Once we get here, how loud are those waves going to be? Not as loud because now you have to spread that energy out over a bigger area. Okay? If you look at this picture right here, okay, these are actually waves made in water, but you're looking at you've got like a glass bottom tank, so you can kind of see it from the bottom. If you look in the middle section, right, you can see there's a real distinct black, white, black, white, black, white. But on the edge over here, you can tell that there's darker parts and lighter parts, but it's not quite as a distinctive change in one or the other. Okay? Because here the energy is stronger and more concentrated, whereas here it's been spread out a little bit more. Okay?
What about reflection? You don't hear it that way.
You could hear it that way too, but what I'm saying is, if that was the case, if this was like the corner of a building and the rest of it was just open, you would still be able to hear it even if there was nothing for that wave to reflect off of. If there is a reflection, then yeah, you'll hear it even better because now you're getting more of that energy coming to your ear. Go ahead.
So you're saying that wave is bending?
Yes.
As it's getting like bigger?
As it's going around the corner. Basically what's happening also, when we talk about waves, like in a one-dimensional kind of thing, like it goes there and it bounces back. And that's what we did with the slinky. But really waves are three-dimensional, right? Like when I'm talking, it's going all around me. And so that energy is spreading out. Like one thing moves the next thing, moves the next thing, moves the next thing. Here, along this boundary, those waves can't make the wall move. But once it gets to here, right, once it gets to this point, now the waves are running into air, right? So they can make the next air molecule move. They can make the next air molecule move. They just couldn't here because of the wall boundary. Does that make sense? So that's why it can bend around the corner like that.
It's not really bending.
Yeah, so
It's not really bending. It looks like it's bending around the corner. But really it's just the energy is now allowed to spread out more than it could before it reached the end of the barrier. Okay. Next, superposition. Two waves can occupy the same space at the same time. Why? Because they're energy. They're not matter. Right? Superposition is down at the bottom right next to reflection, diffraction. Superposition. Two waves can occupy the same space at the same time. We saw this on Friday when we did what?
when do we both of them.
When we did both, yeah, when we standing waves is definitely a superposition thing. But first we looked at it when I had when I was on one side of the spring and somebody else is on the other side of the spring,
So when
right?
they're in the same medium,
Yeah, when they're in the same medium, and we saw when those two waves encounter each other, what do?
they
They just pass right through each other. Okay? There's no change in that. Why? Because they're energy. They don't interact the same way that matter interacts. When matter encounters other things, what do? They bounce off one another, right? Or they may repel or attract, action reaction. Okay? Waves don't do that. Why? Because they're not matter, they're energy. Okay? But what they will do is something that we refer to as interference. Interference is when two waves can occupy the same space at the same time. They have a combined effect on the medium. Okay?
oh we never see this picture.
When two waves occupy the same space at the same time, they have a combined effect on the medium, or the particles of the medium. Remember, a wave is getting one particle of the medium to move the next one, to move the next one, to move the next one. Okay? Waves can interfere in ways we refer to as constructive or destructive. Okay? Which the names sort of suggest what happens to them. If you look at the pictures there, you can kind of see what's going on. Right? I'm running out of time here, so I kind of want to wrap this up. Right? For tonight, what I want you to do, finish looking at these notes. Okay? I will see if I can record the end of this and put it all together so you can hear the whole thing. If you, from the notes, you're not quite sure where it's going on. Okay?
Wait,
Got it?
Yeah.
Good.
Is that picture of those waves that were like up there? Is that what happened yesterday? When
Yep, pretty much. Yes. Yeah. So in this case, Allison, this was when we shook one way, we shook the other way. When they come together, what do you see about the spring at that point? Because of destructive interference, right? But here, right? Amplitude, amplitude. What do you see about the amplitude here? It's bigger because both of them are on the same side. All right, everybody have a good night, or good afternoon, or whatever.
For flat, this, the interference, the up on the left.